ആദ്യം സ്കൂൾ കുട്ടികളാന്ന് പറഞ്ഞു, ഇപ്പൊ പറയുന്ന കോളേജിലെ കുട്ടികളുണ്ട്, കുറച്ചുകൂടി അഡ്വാൻസ്ഡ് പറയുന്നത്. ഒരു ആക്രമണം.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. Good morning.
Sir, start ചെയ്യാല്ലേ sir?
No problem. Start ചെയ്തോളൂ.
Good morning to all of you and welcome all of you to this program. Today, as part of National Science Day, we are organizing this webinar for students and public. Today, our speaker is Dr. M.K. Revarma. First, I will introduce Dr. and it's my pleasure to invite Dr. M.K. Revarma to this program. Dr. M.K. Revarma is a professor in Department of Physics in National Institute of Technology, Calicut. And his research interests are in spectroscopy, development of instrumentation for atmospheric and environment monitoring using principles of optics. He has accepted our invitation and agreed for giving this talk through online. So I heartily welcome you sir, to this program. Today, this topic is spectroscopy, application to Earth observation and climate. Sir, now I invite you to deliver this talk, sir. Welcome you, sir.
Okay, thank you very much. I am going to present a PowerPoint. Are you able to see?
Oh, yes, sir.
Okay. Okay, a very good morning to all of you. I thank Regional Science Center for giving me an opportunity to talk to very young students, and I would like to speak a little bit about spectroscopy in a physics point of view, not so theoretical, but more into a practical application-oriented lecture today. As you know, spectroscopy is a very, very wide area. So even in optical spectroscopy, there are a lot to learn and a lot of things have to be done to apply it into real life. So the title is very big: spectroscopy application to Earth observation and climate. But obviously we will not cover entire topic. In the first half of the talk, I would talk about very, very basic optical stuff, that keeping in mind that we have very young minds from school in here. And the second half, I will work a little bit more on presenting you the kind of research that we do, like simple applications of those. And our big picture is always the climate, and what we do one way or other is going to apply to the climate scenario of the Earth. So I call it Earth observation. So I want to remind you the basic, and we also, the way I want to present it also is influenced by the fact that often we find students coming into our institutes with very good basics, very good marks, but yet a bit of confusion remains here and there about different spectroscopic parameters and the measurement parameters and the outlook of their understanding. So for those who already completed your school and are in colleges, you probably have done some spectrometer experiments using prisms to find the wavelengths and etc. like that. With that little bit of introduction, and I would like to start with the tribute to the greatest Indian spectroscopist, Dr. C.V. Raman. And obviously, we commemorate his accomplishment for the National Day celebrations. So let me start with the most amazing natural prism that we see every now and then, that is the rainbow of images. So obviously the spectroscopy has a word spectrum in it, and the spectrum here refers to individual wavelengths or the colors of the natural sunlight. So sunlight, we have the white light coming from sun, and white means a combination of a set of colors, and different light has different wavelengths. I am coming to that into the next slide. And our eyes have single detector and effectively, and we see the intensity of each of them as a sum of each of them. So if you look at that, we see, or we take light as an electromagnetic wave. So light has already, just as an introduction, I would like to point a few things out that might be interesting to some of you. So everything happened. A lot of inventions in physics happened because of the puzzling nature of the light. Light has been a topic of study by so many great physicists since hundreds of years. So let me put it this way. To make it short, light was considered as a particle before. At the same time, light was considered as a wave, and then people tried to think them as a particle. They have their own. They have their own. Oh, sorry, I jumped. So they have their own reasons to believe so, and then those who think that those who thought that they are purely waves, they had their own set of reasons to believe so. So you can see that people, they were really arguing with each other, and they were coming up with theories supporting theirs. And if you think of development, even quantum mechanics, the basics of quantum mechanics came from the fact that some of the things, for example, black body radiation. Yeah, black body radiation was never quite understood until Planck gave Planck's law of black body radiation. So there, you had to have little packets of waves, h nu with energy h nu is the frequency of the light, and then special relativity came, where the speed of light is a constant. It's not like you can walk and there's a train going, and if you combine the speed of the train minus speed of the walking or a car, it gives you the next speed. That doesn't work in the realm of light, speed of light. So speed of light is a universal constant, and the transformation going from a moving car to a moving train is Galilean transformation, and the transformation going from very fast moving objects, it gives Lorentz transformation. So these transformations also came about fundamentally studying these aspects, and that actually constituted a lot of fundamental inventions in physics. I don't want to go much into that. Now we have light as a electromagnetic wave, and the shorter the wavelength, the color going to bluish and violet, and they have more energy. On the other side of the spectrum, so that's oops, I am okay. So So this side, higher energy, this side, lower energy. Are you able to see the writing?
Yes, sir.
Okay, lower energy waves. Longer the wavelength, lower energy. Larger the wavelength, higher energy. And visible light. And this is the visible light. We saw visible. We call it visible because it is our eyes are sensitive to those radiation. And but the electromagnetic radiation is actually having an entire spectrum of very short, very short gamma rays into radio waves, and each of them have their own applications and etc. So the light, the way we want to apply it is into the spectroscopy is that we see the is this, you have light, you have to detect it, right? So light comes and falls into our eyes, and what we see is the sum of intensities of all the light waves in it, the entire spectrum of light in it. So you have a spectrum.
So that slides are not changed, sir. We are seeing the first slide now. Same slide, sir.
Oh, it's not moving?
Yeah. Only we are seeing that first introduction slides.
You still introduction slide. Oh, okay. Let me see. Maybe it's the. I don't know. Let me see.
No. Yes. No. What is spectroscopy? No, just come.
Oh, I don't know why is the reason, I do not know. Now?
Now it is clear, sir.
Yes, sir.
Now it is switching?
Yes.
Yes, sir.
Right? Switching, right?
Yes.
Okay, good. So we want to get a spectrum of light, meaning each of the colors should be separated. If you want to separate the colors, you want to use a prism or a grating or a color filter, etc. So how do you get different spectrum? So fundamentally we have two things. One is dispersion. Oops, jumping. One is dispersion by a prism, and the second is diffraction by a grating. So these are all optical phenomena: dispersion, interference, diffraction, etc. So we will not go much into that because I want to talk more about the practical aspects. So we have two ways you can split the light waves into two for spectroscopic applications. One is using a prism. So the white light will fall on a prism, and it will undergo dispersion, and out you will see or if it is a natural sunlight, you will see violet, indigo, blue, green, yellow, orange, and red. And if you have done a spectrometer experiment, you would have seen all of those, and you would have measured your spectrometer readings by rotating and looking at each color, and then eventually find the wavelength of that. So if you look at this, you can see that the one with the shortest energy undergo largest deviation from the path. Now, if you look at the diffraction by grating is nothing but gratings are nothing but a piece of glass and a lot of lines in it. Okay, a lot of lines in it. So if white light falls onto that grating, then each of these scratches, the lines, actually diffract the light, and then you can see a spectrum of light on the other side. But you can see that the largest deviation comes from the long wavelengths, and so that's the difference between these two optical phenomena. But you can see that you can take the white light, you can somehow split them into a spectrum of wavelengths. So you can individually detect. Obviously, that brings us to the point that you have to have something here that detects each color. Either way, whichever way you want to have your instrument, you should have a set of detectors so that you can measure what is the intensity of red light, what is the intensity of blue light, like that. And whether you want very good detection limit, or that depends on your application. So we'll come to a discussion for different applications, what are the kind of detections we would like to use. So basically you can have array of detectors, or if you are using prism or grating, you can have one detector and then rotate this grating. So if you rotate the grating, then you have one detector, and one detector can detect each wavelength as you rotate it. That also is another possibility of detection. Many instruments will have rotating grating. Then you have to measure one wavelength at a time, one color at a time, and you have to sequentially measure it one after the other after the other. In this scenario where you have an array of detectors, you can measure all of them at the same time. So both has its advantages and disadvantages. So what do you get if you put a array of detectors? They are called usually diode arrays. There are different detectors for different wavelengths. There are silicon diode detectors, indium gallium arsenide diode detectors for near IR, or they are there are photo multiplier tubes, but you will not have an array of those. So if you have white light coming, if you have white light coming, and if you have white light coming and you get a grating and you get a spectrum, you will get suppose you want to plot a graph. You know what is meant by plotting a graph. So you put wavelengths on your x-axis. You measure the voltage that array measures, or you call it intensity of the light. So intensity of the light. So you will get a line like that. Yeah, this is a line, and each line here is actually shown. So the maximum in this light is given by red, or near orange red, and there is another big blue is also there. So this is actually an emission spectrum of LED. So LED is a light emitter. Okay, so emitter and emission spectrum. So these are the light coming out of that, and you make you put a grating and you make a diode array, and you get a spectrum like that. So this like a light source, a grating, a light source, a grating, and an array of detectors. Maybe you can have lens, etc., and that is called a spectrograph or a spectrometer. So a spectrometer separates light into constituent wavelengths. So the spectroscopy is study of some parameter that is based on this particular aspect, that you take the light, you split it, you measure a wavelength, or you measure the intensity of different colors of the light, you get a spectrum, and from the spectrum you try to study something. Okay, so in this aspect I would like to say one more thing. We said that grating is a glass with a lot of lines. Yeah, so what if I have two gratings, one with some number of lines, one with almost double the number of lines, okay, or maybe 4 times the number of lines. Here it is 300 lines per millimeter. There is 1,200 lines per millimeter. So the light is incident, and it is you get you see there is an array of detector. It didn't change, but you increase the line, you see it is.
Lights are not changed, sir. The same. Still.
Oh, lights are still not changing?
No.
Oh, I don't know. Maybe it's internet issue. Okay. Let me go out again and come back again. you see this?
Yes.
What is spectroscopy? Huh? Now you change. You see that this thing's changing.
That's dispersion.
Okay, it changed. I was talking about this. It changed, right? Spectral resolution. You see a slide called spectral resolution. No. Hello.
No, sir.
It's not.
Dispersion by
No, sir, it's
diffraction.
the dispersion and diffraction.
Dispersion and.
Diffraction.
Oh.
Now it's showing fifth slide.
It's changing.
No, sir.
No.
I don't know what's happening. Maybe.
Okay, so spectral resolution.
Because I am using 8 seconds. Just bear with me for a second.
Sir, are you
How about now?
using the window sharing mode or just sharing the entire screen?
Now it is Windows sharing mode.
Okay, I think sometimes some errors used to occur in the window sharing mode. I think the entire screen sharing will be somewhat more stable.
Let me- Oh, it's okay.
It's fine, sir. Perfectly fine.
Okay.
Yeah, fine, sir.
Okay. So I think I was drawing on the screen. I had a second screen where I could draw. Now I removed it. Now I cannot draw. Now I have to. There's no drawing. Okay. Okay. So if you have a spectrometer, you get a spectrum. In this case, this is a spectrum measured by a spectrograph, which consists of a light source, a grating, and array of diodes. Now, if what happens, I mean, I am talking mostly on the point of view of an instrumentation, because I develop instruments for the principles of spectroscopy. So you can ask, what if the light source is changed? Obviously the spectrum will change. It might peak somewhere else. If you have just the blue LED, it will only have the blue, rest will not be there. And now I can ask, what if I change the number of lines in the grating? So here, if you change the number of lines in the grating, you can see on the left side that is 300 lines per millimeter. On the right side, you have 1,200 lines per millimeter. So what is the difference here? The width, you know, in the first case, if you have maybe 1024 diodes as an array of the detector, and then it'll contain an entire violet to red. The entire spectrum is contained in there, and if you almost 4 times the lines, you have increased 4 times the lines of the gratings, what happens is that both sides of the spectrum is lost. That means the spectrum you measure has a higher resolution. The spectrum you measure in this case has a higher resolution. So what is the resolution means, I will come in the next slide. So the splitting of the light into individual wavelengths is better in the second case, and it's less effective in the first case. So every spectrometer that needs to make a measurement of a broad spectrum, like the entire visible range or any other part of the electromagnetic spectrum, would actually need to specify its resolution. And what is the effect of the resolution? How does it reflect in our measurements? That is the next slide. So you look at something here. Here, it's only in the red part of the deep red part of the spectrum, that is 755 to 775, very, very small region of the spectrum. Now, if you look at the black lines, that is more like the second part of the second side, very high resolution. And the red line would be something like the left side measurement. So you see, so you can see a lot of, different lines much clearer when you have higher resolution. When you have a lower resolution, you still by and large see the effect of the presence of oxygen. This is the oxygen spectrum, but this is not an emission spectrum. Obviously, this is an absorption spectrum because the intensity has been absorbed. Whether it is emission spectrum or whether it is an absorption spectrum, you can see the effect of a spectral resolution. So the instrument that needs to measure the spectrum should have a better resolution, but then you compromise the range of the measurements. This is only showing a very small common range of the measurement. So that is about the resolution of spectrum. And when we talk about the spectrum, there are the spectrum is due to the interaction of light with matter. And everywhere you have energy lines, and you know that if energy is applied to an atom or a molecule, it will go from one energy level to another energy level. So in the left side, you can see that light is absorbed. So you always need to give light the specific amount of energy, exact specific amount of energy that needs to go from one ground state to an excited state. So it takes light or any other form of energy to get excited from a lower level to a higher level. And in the middle, you see that the light can, the molecules or atoms that are in the higher energy level can lose this energy one way or other, and then they can come back and relax back to the original lower energy state. So absorption is there. So there are a lot of other ways. The light is interacting with matter. Light is absorbed by the matter, it gets excited. Light is released by the matter, it gets relaxed. So light interacts with the matter, and the effect is the light either absorbed or emitted. So when you make the measurement of a spectrum of a light, then you can see, like I said before, if it is an absorption, then the intensity is lost. If it is an emission, then intensity is raised. Okay. So having said that, there is one more interaction of light with matter called one more interaction of matter that is called stimulated emission, right? And you are very familiar with the kind of light sources that give stimulated emission, and they are lasers. So what is the difference between the other light sources and the laser? So very briefly, in an instrument point of view. So this is an example of helium neon laser. So you can see the picture of a helium neon laser. The light is coming out just like a thin ray of light and a very specific color. This is not like the natural light with it's like a white. It's not coming out like a white light. So what happens here? So this is helium neon laser. So it contains helium and the neon in that little instrument. So obviously, one way or other, you get the atoms or molecules inside that little volume excited, And so if you look at, there are two energy level diagrams above that little instrument. On the right side, you can see the excited, just like the previous this particular picture, where excited atoms or molecule can relax by emitting light. Here also you can see the molecule getting relaxed by emitting light. So particularly interesting here is 632.8 nanometer. That is the red. It is so the nanometer is the wavelength of the light in nanometers. Sometimes we specify the wavelength of the light in angstrom units. That is 10 to the power of minus 10, and a nanometer is 10 to the power of minus 9 meter. Okay. So 6,328 angstrom or 632.8 nanometer is the emission wavelength. So you can see that one specific transition of between two levels. So obviously it can have only one single wavelength of emission. So that's very, very crucial and very useful. And you can see the spectrum of the light on the right side, the top, you see a very sharp line. Now coming to this picture, you have a spectrometer. You want to measure the emission line of the light source, and you have a lower one and lower resolution spectrometer and a higher resolution spectrometer. So in this picture, you will see that the top one will be something like measured by a high resolution spectrometer, and the bottom one is something like some lower resolution spectrometer measured. You see the width. So the grating or prism or whatever you used to disperse the light into different wavelengths have much more effectiveness on the top side, and much more closer to the reality of the emission source of the laser, whereas the lower resolution measurements below are not properly resolving these lines. We call it the resolution of the lines, so resolving the lines of the emissions, or specifically separating each line from the emission source. So that's not happening here in the lower resolution spectrometers, and higher resolution spectrometers have much better it's closer to the reality. So that's another instrument aspect. Those who do experimental physics will know. So that's all I want to talk about, the basics of a spectrum, electromagnetic spectrum, light spectrum, and its dispersion and its detection. Now going to applications. What I am trying to say here is that you can always make a spectrograph, a spectrometer, and then you look at the light coming into it, and you can always learn about something from where it is coming from. So this is an application very readily available, or very commonly used for very basic lectures. So this is an application in astronomy. You look at very far away stars. So the light coming from the star. So this is actually from S7 spiral galaxy. So the light coming from there, you can use a prism or a grating, and then you use a spectrograph array of detectors, and you get a spectrum. So the schematic of the instrument is above. Actually, instrument doesn't look like that, but this is just to show you the components in an example of those. And below, you can see in the graph, you can see a lot of lines. The one sticking up is always emission lines. So, and the one actually few dips from the baseline are actually absorption lines. That means the light is coming, and some molecules are there on the way, or a dust is there on the way, or whatever is on the way, and it is taking the light out of it, so that is absorbed there. So you can look at the spectrum from a faraway star, and you can see what are the emission lines, what are the absorption lines, and you can say what the star is primarily constituted of, because every molecule, just like the oxygen molecule spectrum I shown, every molecule, every atom, they will all have a specific wavelength that they would like to absorb or emit when they are in an excited state. So this these lines can be looked at, and we can say, oh, we have these gases in that particular star. And another thing we can say is that, okay, so much light is absorbed on its way to here, so there may be some interstellar dust or gas or whatever is absorbing, and if we know at which wavelength they are absorbing, we can say, if we know that, then we can say that, okay, these gases are there present in that planet or in between that particular star and our planet. So this is an application of a readily direct application of spectroscopy by if you can make a spectrometer that can measure the spectrum of the light that is coming, then you can always do a ready application of this. So coming to the second part of the talk, I would like to quickly say that every black body radiates light, and that's where we get the light. And sun is a black body. It has a temperature of less than 6,000 degrees, okay, maybe 5,500 degrees Celsius. And then if you can have a spectrometer, take it up into the top of the atmosphere, and if you make a measurement of the light spectrum, and here you will see the black line you see is a black body spectrum of Planck's law specified black body radiation, black body emission spectrum of something that is about 5,250 degrees Celsius, hot, very hot. So the hotter it is, the peak of the emission goes to smaller wavelength or higher energy. So in this case, if you make a spectrum, or if you make a measurements on the top of the atmosphere, the yellow is the spectrum that you are going to measure, and you can fit it very nicely with that 5,250 degrees Celsius black body spectrum. Now you come down to the sea level and you make another measurement. Look at that, and you put it on top of the measurements you made on the top of the atmosphere, and then you see the red one that is making the picture. So you can see that whatever is there between the top of the atmosphere and the sea level is actually either added by the atmosphere or taken away by the atmosphere. Here you can see it's mostly taken away by the atmosphere, and you can see that pretty much everything below 350 nanometer is gone, or 3,500 Armstrong is gone, and that is because of the ozone. We know that ozone, there is an ozone layer in the stratosphere 26 kilometers above the ground, and that is actually a lifesaver for us. Ozone in the stratosphere is not a pollutant, it is a lifesaver. It absorbs all the UV that is coming in, it prevents the UV from reaching the surface of the earth. And so if you measure it below below the atmosphere or the sea surface or sea level, then you see a lot of UV missing, and then you can see a lot of other dips in that. All those dips are absorption lines. So this is an absorption spectrum. So the yellow you see up there is an absorption spectrum of the gases that are in the atmosphere, and primarily they are water vapor, carbon dioxide, and you can see oxygen line. The oxygen line I showed you before is already seen there near 750 nanometers. So you can see spectroscopy has another direct application. What is in the atmosphere? All you need to do is to make a measurement, and you can say, there's a lot of other things in the atmosphere also, but this is a water vapor and the carbon dioxide, they are there, and you can see that water vapor and carbon dioxide are greenhouse gases. They are the water vapor we don't consider because we need water vapor of that, but more water vapor, it gets more warmer. Another application of the spectroscopy is looking at the atmospheric opacity. Why do you want to know things like this? Because if you look at this, the visible light spectrum is there. Imagine if the atmosphere is absorbing a lot in the visible. It does absorb a little bit in the visible, but if it is absorbing a lot of light in the visible, then that means the sunlight is never going to reach the surface of the earth, and we need sunlight, and the sunlight is the peak of, you can see the peak of the spectrum is about 550 nanometer, which is the green. Okay, and you can see that our eyes and pretty much every living things that use direct sunlight will have the peak sensitivity at the peak of the sunlight to be more efficient, and our eyes are also more sensitive to 550 nanometer. So obviously atmosphere is transparent to most of the visible, otherwise sunlight wouldn't reach here. Now if you look at a very short wavelength, they are all blocked by the atmosphere, and that is very good, otherwise we would not be able to survive in this planet. And if you look at a big gap on the right side, about I don't know, 8 centimeter to about 20 centimeter, then you can see that a wide open fully transparent band of the atmosphere. So we use that for so they are from they are the radio waves, and all the radio waves in that band is actually transparent. The atmosphere is transparent to them, and that gives us a way to observe far away objects using radio waves. Okay, so see, obviously we want to know which bands will transmit to the atmosphere, which band will are blocked by the atmosphere. Otherwise we wouldn't be able to use our day-to-day instrument like radio or television or satellite communication or even mobile, because if any of those wavelengths that we want to use for our electronic instrument is blocked by the atmosphere, obviously we won't be able to make those work. So this is also an application of spectroscopy. Okay, coming back to what I would like to do every day is to look at the big picture, and the big picture of our Earth in that context is climate. What is climate? Climate is a component. I mean, climate is a composite of a lot of components, and the effect of those are giving us a shift in the climate. Once we are I mean, we are very familiar with seasons and rainy season, spring season, cold season, winter, whatever. Yeah. So we do this change. We do see these changes every day or every few months, and then it turns around and repeat every year. So we are in sort of a equilibrium condition, meaning you take a ball and put a little bead in it, so it will stay in an equilibrium. But if you turn the ball upside down and keep the bead on the top, then you are in an unstable equilibrium. Bead will simply run away from the top of it's like a hill. You put a ball on the top of the hill, it will run away from there. So that is an unstable equilibrium. But if it's in a like a valley, the ball will stay there. So that's a stable equilibrium. So what will happen if you disturb the stable equilibrium? It will oscillate about the mean position, right? So it will oscillate about the mean position. So first we have to look at the component of the climate. Everything should be where it is, and all are in the mean position, and suddenly disturb it a little bit. Then what will happen to the climate? Meaning the effect of the climate will be forcing the Earth system to move away from equilibrium. So this may sound a little bit abstract, but that's what it is. So to give you a simple example, you increase the carbon dioxide in the atmosphere, what will happen? The outgoing radiation, the infrared radiation is absorbed by the carbon dioxide, and it will warm the globe. So that is moving away from the current situation, which is an equilibrium, to a warm condition, that is the global warming. So a lot of these components, solar input, there is ice, there is ocean, there is land, there is vegetation, volcanic activities, cloud, rain, everything. Each one of them has its role to play, and any shift in any role of any of these components, they change a little bit, it will change everything. Primarily, you know that we everything everything in the earth is sustained by the energy from the sun. And if you look at the way we receive the energy, the earth is intercepting the light from the sun, and more energy is received by the equator, less energy received by the polar region. So equator is always warmer, polar region is always colder. So what happens? Earth's atmosphere and Earth's ocean continuously try to move such a way that's like a heat engine. It goes such a way that it will try to transport the energy from the equatorial region to polar region. So that create wind, that creates cyclone, that create a lot of disturbances in the atmosphere, and it transports about 6 petawatt, 10 to the power of 6 times 10 to the power of 15 watts of energy, joules of energy per second from equator to poleward. So a lot of energy is being received by the earth, a lot of energy is being transported from equatorial region to the polar region. So all the energy is received in the form of electromagnetic radiation, and then it heats things up and it moves around. So that's the climate system. To give you a brief of that, you have incoming solar radiation in the visible side, outgoing, I mean, Earth is not as warm as sun. So Earth radiates as a black body in the infrared. Sun radiates in the visible light. So sun is very, very hot. So some light receives on the top of the atmosphere, some light is lost in the atmosphere, and some light is reaches the earth, and some part of it is absorbed, part of it goes back, reflected by the cloud. So that happens in the visible side, and then earth takes absorbs some energy, it gets heated up, it transfers heat into the atmosphere by conduction, convection, and also radiation is in the infrared. So a net effect of this is constituting our equilibrium in climate. Now if you disturb any of those, for example, intensity of the light coming from the sun is reduced a little bit or increased a little bit, what will happen? It disturbs the system. So it is going to force the climate system to move out of the equilibrium to a new equilibrium. It can be global warming, like we are facing now. You put more carbon dioxide into the system, you force the system to go to the warmer conditions. So new equilibrium will be on the warm side, otherwise new equilibrium will be on the cold side. Okay, so there is world there's a committee called Inter-Parliamentary Committee for Climate Change. It's by the United Nations, and the United Nations IPCC actually brings out report every year. For every component, you can see on the top of the list is carbon dioxide. It is red in color, meaning radiative forcing is to the right side of that line in the middle. So it is creating 1 watt per square meter, 1 joule per second per square meter, and Earth has a lot of area. So carbon dioxide is a primarily reason for forcing our system, radiative forcing our system to the warmer climate. But there are other things which are in the blue that may be pushing us into the colder. So this is the big picture. Now what can spectroscopy do to look at the big picture, or try to learn what is going on in the big picture? So that is where the application of optics and spectroscopy into the picture. So I think I will not go too much into detail, but I will just give you a glimpse of what we do, and in an instrumentation point of view. So what we are trying to discuss here is the way an optical instrument person look at light and try to find a way to measure the light, whether it is from a laser source or it is from a broad visible lamp or anything, or even a solar spectrum, and see where it fits the spectrum, the study of the spectrum, where it fits to learn about the thing. So one thing we have not discussed so far is the scattering of light. So light is coming, so a little wave of light is coming, you have a particle there, or a particle can be a molecule, or can be a dust particle in the atmosphere or anything. So light gets scattered in all directions. So there is light, incoming light, outgoing light, and scattered light. Now scattered light is also, if it is a white light, scattered light is also a white light. If it's blue light, scattered light is also blue light. So if you can measure the scattered light, that can give us some information. What information that can give us? This might be a little bit of interesting. So there are several kinds of scattering: elastic scattering, inelastic scattering, and quasi-elastic scattering. We are not going to go into that in detail, but I can say that Rayleigh scattering, that we are all very familiar with. Why the sky is blue? Due to Rayleigh scattering of visible light by the gas molecules. So that is an elastic scattering, and Rayleigh scattering is actually a bit more generalized to give something called the Mie scattering by Gustav Mie, a German scientist in early 1900s. So he generalized that theory, and Rayleigh scattering is a special case of theory of light scattering. So Raman scattering, C.V. Raman discovered that, the Raman effect. Raman scattering is an inelastic scattering. Just to give you, inelastic means incoming light have a different frequency than outgoing light. That's what the wavelength change, the light changed color when it went out. So if you look at the atmosphere, climate system, and if you look at an observer, you stand in the somewhere and look at the sun at different time of the day in the different conditions, you can see that Rayleigh scattering gives you blue sky because it has a nearly the same amount of light scattered in all directions, and blue scatters more, and you see sky as blue. But in the horizon, when sun is rising or sun is setting, you see it as red because there are more particles in it, and then blue is lost and red comes to you as an observer. So that is explained by Mie theory of light scattering. So you can see that light above you see more blue light when sun is right in front of you at the horizon. That gives you more different color, red. However, this is not always the case because Mie theory of light scattering says particle size actually matters, because if you have a different size of particles in the atmosphere, you could technically see a blue sunrise or sunset, and this is actually a picture taken on the Mars. Look at the Martian sunset. Mars obviously has a lot of particles in it, but sunset looks blue. So that's amazing. So specific size of particles that is in the atmosphere can give you different colors. So that is also an interesting observation by spectroscopy. So it is possible to have blue sunsets and sunrises instead of red one. And we have also heard of the expressions once in a blue moon. The moon can also turn blue. It's also because of the presence of specific particles in the atmosphere in between your eyes and the moon. So these are the effects that we see in our nature in a spectroscopist's point of view. Now, what are the considerations of the spectroscopist to look at this and measure the light? Okay, that we have already discussed, and just 5 minutes I would like to take the kind of instrumentation that we do. How do you make actual instrumentation and how do you measure things? So basically, as I said, you have a light source, you have a detector, and then you have everything in between. That is our sample, whether it is atmosphere, interstellar dust, or Mars. It doesn't matter. There is always a light source and a detector. A detector can be one detector or array of detector. One detector is like our eye. Array of detectors needs a dispersion or a diffraction in equipment like a prism or a grating, so that you can get the spectrum of light. So there is something called Beer-Lambert law. I'm not going to go into that. Spectroscopists always use to quantify the light that is absorbed or scattered or whatever is quantified using the Beer-Lambert law from the measurements. How much light is transmitted, how much is absorbed, how much is scattered, is given by Lambert Law or Beer's Law. So you can have different kind of sources. You can have diode lasers, you can have UV lasers, you can have a little bulb, LED, anything. So you can have light source and a detector in one place, or light source and detectors different place, light source and detectors kilometers apart. A lot of different kinds of instrumentation are used in observing our Earth climate system and all the wavelengths. But you cannot have a universal instrument which covers from gamma rays to radio waves. Your light sources are characterized by emissions at certain wavelength band, and your detectors are sensitive to certain wavelength band, just like our eyes are sensitive only to the visible light, and we will not see infrared or ultraviolet light. Even though they could damage our eyes, we will not be able to see them. And you may have heard about Michelson interferometer. Michelson interferometer is a different and very complex instrument, and one of the best spectroscopic meter that physicists have made. And if you remember, Michelson is the only Nobel Prize winner who got a Nobel Prize for a negative result, because he created the beautiful instrument to try to measure the wave nature of light, thinking that the wave nature of light requires a medium to travel, and he was looking for ether. The ether was not, he thought that ether is pervading the universe, and the ripples in ether are light that we see. But unfortunately, Michelson was not able to measure the ether. It was a negative result experiment. However, because of the beauty of the instrument that he created, it requires a lot of mathematical procedure called Fourier transform, and so I'm not going to go into the details of that, but it's a very beautiful instrument created by Michelson, and Michelson got a Nobel Prize for a negative result, and the only person who got negative result. So the research can give us a positive result or a negative result. Nevertheless, it is a curiosity of mankind that leads us to the research, whether it is positive or negative. If you know the result, then there is no point in doing the research. Anyway, I'm simply scrolling through this. See, and applying to real life monitoring. This is a pollution monitoring system where we use Fourier transform infrared. So we can use in the real-time scenario. We can calibrate the instrument. We can measure actual pollutions, whether it is particle or gas, carbon dioxide or anything, and we can actually characterize the emission sources, and we can correct it. So some algorithms are necessary to do that. Not only the infrared, we are also using the visible, and we can have a lot of spectrum. Different molecules have different absorption spectrum. For example, nitrogen dioxide in the brown, they can also have. So if we know the absorption spectrum of the molecule, we can actually measure them, and we can study them. We can study the reaction. We can study the contribution, and just simply quickly say giving another measurement we made. There is some plants called sea algae, or we call the seaweed, and seaweeds emit iodine. All the living beings, including us, have iodine content in our body, and when we get stressed, we release iodine. That's a biologist's theory, and we actually tried to test it with. So this is a Cork Harbor in Ireland, the last place Titanic ever came. That's another. I didn't want to go there, but we went and picked up some seaweeds, the plants during the the tide. When during the tide, all the water will rise, all these plants will come into the shore, and when they retreat, they will get stuck in the store. So we picked a few of them. We brought to the lab. This is a seaweed. We brought to the lab, and 1% dry weight of it is iodine. So it's a lot of iodine content. That's why we picked the plant. And we brought it to our lab. We had light source, we have light detectors. Light source is within our lamp, and the detector is a CCD array spectrometer. We put it, we measure without sample, we measure with sample, we use some equations, and we find that iodine, the ice emitted in huge numbers. You see little puffs of iodine until in about 24 hours later, the seaweed was dead. but it is getting oxidative stress and it releases iodine. So see, that's another spectroscopist point of view is a interesting thing. And a plant biologist would be very interested to know how this measurement is made, and a time series of these measurements can be useful in studying the plant. So it's also this iodine in the atmosphere is also important for our climate studies. It's also important for the biologist point of view. So one thing we learn from this is that every living being, when they are stressed, releases a bit of iodine. So instruments are deployed. I don't want to go too much into detail. So instruments are deployed, measurements are made, again, light source and a detector and a spectrum. And from the spectrum, we measure what is in the atmosphere. In the big picture, we plug into the big picture and see what is the radiative forcing that is going to do to the climate. I am not going to go. So one last important event that I want to point out to you is that we had a total solar eclipse on December 26th, 2019. I'm sure the planetarium had its telescopes that was available for everyone to view. We also had a small telescope we developed here. And what we did here is that we took our spectrometers to the Parliamentary stand in Calicut, and we saw that there was a lot of ozone variation, because ozone is a pollutant in the troposphere, and ozone and nitrogen dioxide, which are primarily coming from the vehicular pollution, actually is reacting with the sunlight, called photochemical reactions, and then their concentration was found to vary during the total solar eclipse. So we got a rare chance to measure those things, and we measured ozone. On the left panel, you can see the ozone was there's a dip in the ozone. In the red curve, you can see that exactly at about 9 or after 9, you can see that the dip in ozone. So that means sunlight was not available and ozone was not produced. So some pollution dynamics was there, and it was, again, our spectrometers measured this. We have already published this as a paper. We also our spectrometer also tried to measure some burning happens in the Parliamentary stand. This is a measurements of nitrogen dioxide and glyoxal. Glyoxal is a pollutant that is formed by burning woods. So we saw that the vegetable market in the Parliamentary stand, actually there was a lot of wood burning happens, probably the boxes of tomatoes or things like that. And then in the night, you can see that 3 a.m. in the morning and 5 a.m. in the morning, we see a lot of vehicular activities at the vegetable market, and then that creates a lot of glyoxal kind of pollutions from the burning. So this is another application that we directly did. Pyrogenic means the burning of the woods. So we found that as well. So I hope I could give you a small glimpse of instrumentation point of view of optical spectroscopy and its application that we are trying to do at NIT Calicut. I would like to stop here and invite any questions you may have in your mind. Thank you very much.
Now participants, they can ask questions now. If you have any doubt, you can just ask or type it in the chat box. think nobody is asking questions. So, like to conclude this session, sir?
Yes, go ahead.
Okay. On behalf of Regional Science Center and Planetarium, I would like to express our sincere gratitude to Dr. M.K. Rivamma for giving this wonderful lecture, because he has explained everything about what is spectroscopy and its application in our daily life. So, for this, let's say for this solar eclipse, they conduct one experiment. There is a new knowledge for us, because we also did so many activities here. So, in daily life, what is the application of spectroscopy? There is, enormous applications are for this spectroscopy. Okay, sir. Thank you for spending your valuable time here, sir. Okay. Till again.
Thank you very much. Thank you. Bye.
Thank you, sir.